So now let's jump into the energies. All right. You can be asked, right? Okay. What does diagonal line represent? What does the horizontal line represent in terms of phase and phase changes, right? But you can also be asked what's happening in terms of kinetic and potential energy. So I'm going to define those guys, okay? So I'm going to write it over here, okay? Kinetic energy, KE, okay, is energy related to motion. So you make a note of that, okay? So it's energy related to motion. Alrighty? And potential energy, what's potential energy? Potential energy, yes, is either stored, okay, energy, or energy related to position. Okay, so potential energy is either stored energy or energy related to position. Alrighty. So what's happening? Let's do the easier guy. Let's do kinetic energy. We know, hopefully from experience, right, that temperature is a measure of average kinetic energy. Let's write that down. Okay, so temperature, T, EMP for short, is the measure, okay, of average, ABG for short, kinetic energy, KE. All right? So very, very, very important definition, all right? Temperature is a measure of average kinetic energy. Now, at the flat lines, let's deal with that. At the flat lines, what do we notice? We notice that the kinetic energy will be staying the same. How do we know? Because temperature is also staying the same, okay? So if they ask on a quiz or test or whatever, at what point or what section on this graph do you see kinetic energy staying the same? You simply look for the flat lines where temperature is staying the same. You go from there. You don't guess. You don't mix and match. Okay? You analyze and you go from there. Okay? And it's very obvious and simple for you. All right. Now, what happens sometimes, guys? The potential energy sometimes, is a little bit tricky for students. So I'm going to try and analyze that. Now, I tell my students, okay, if you're analyzing potential energy and what's happening, okay, simply look to see, right, what the particles are doing in terms of their proximity, in terms of how close they are to each other. Now, we notice over here, when we're going from a solid to a liquid, right, when you're melting something, okay, what are you doing? You're separating the particles, all right? So what happens there? Draw some particles right here. Okay, alrighty. Now, if you're going from a solid to a liquid, right? Do we agree or disagree that the particles are separating and you need energy to separate those particles? The analogy I sometimes use is like you're blasting a water cannon into a crowd of protesters, okay? And some students are protesting that they want more homework, and the deans come out and they blast them with water, right? Okay, just an analogy, right? Okay, so the students are doing what? They're absorbing water and they're scattering, okay? So the same thing, this guy right here, this solid, is absorbing, okay, energy and separating to make the liquid. Now you notice, right, at melting, the kinetic energy is constant because the temperature is also constant. And I told you guys before, if one of the energies is doing something, the other one's gonna be constant, okay? So in this case right here, you can think of it as kinetic energy resting or constant, and potential energy having to do something, all right? So what is potential energy doing? Potential energy is increasing in order to separate the particles. So when you see, guys, make a note of this, when you see at a phase change, whether it's melting or boiling, particle separation, that's a good indication for you that the potential energy is increasing. And it's clear to us that the kinetic energy is constant or staying the same. Okay, moving on. Now, we notice here, guys, okay, at the diagonals, right? Do we agree or disagree that temperature is increasing? Okay, we see that bam's going up, bam going up, bam going up, right? So make a note of that. At your diagonals, right, your temperature, okay, is increasing. Therefore, your kinetic energy also also increases. So make a note right there, okay? Alrighty. And at the phase changes, we notice that the temperature is CONST for short, constant. So your kinetic energy is also going to be constant, all right? They're both constant. Now, once again, work is being done. How do we know work is being done? Because the particles are separating. So potential energy at the phase change, use a different color here, potential energy is increasing at the phase change lines to separate the particles on a heating curve, okay? Alrighty, so we'll move on in a second.